In this section, we are learning about radian measure. Degrees and radians. Degrees and radians are the two most common means of measuring angles. Degrees are used to express directionality and angle size. If you stand facing directly north, you are facing the direction of 0 degrees, written as 0 with the degree symbol. If you turn yourself fully around so you end up facing north again, you have turned through 360 degrees. That is one revolution, or one circle, is 360 degrees. Radians, abbreviated RAD, are the metric unit measure of an angle. The radian measure may be defined as the ratio of an angle's intercepted arc to the length of the circle's radius. So here's a circle. This part of this angle that is on the circle is called the intercepted arc. So the radian measure for this angle is the ratio of this intercepted arc length divided by the radius of the circle. That gives us the radian measure of that angle. This symbol, theta, is often used to represent an angle in geometry. The intercepted arc of an entire circle, which is one revolution around the circle, is the circumference of the circle. So if the angle goes all the way around, then the intercepted arc is the circumference of the circle, or 2 pi r. Therefore, the radian measure of the entire circle would be the ratio of the intercepted arc, which is the circumference, over the radius of the circle. So we get 2 pi r over r, which then reduces to 2 pi radians. So the whole circle has radian measure 2 pi. Then, since the degree measure of an entire circle or one revolution is 360 degrees, it follows that 360 degrees equals 2 pi radians. Side note, why do we have to learn radians when we already have perfectly good degrees? This was taken from Purple Math. Because degrees, technically speaking, are not actually numbers, and we can only do math with numbers, this is somewhat similar to the difference between decimals and percentages. Yes, 83% has a clear meaning, but to do mathematical computations, you first must convert to the equivalent decimal form 0.83. Each of radians and degrees has its place. If you're describing directions to me, I'd really rather you said turn 60 degrees to the right when you pass the orange mailbox, rather than turn 1/3 pi radians at that point. However, if I need to find the area of a sector of a circle, I'd rather you gave me the numerical radian measure that I can plug directly into the formula, rather than the degree measure that I'd have to convert first. So, similar to how we convert percents to decimals when we want to do computation, we can convert degrees to radians for computation as well. You won't always be given angle measures in the form you'd prefer, so you'll need to be able to convert between radians and degrees. We're going to learn how to do that in just a moment. Since a full circle of 360 degrees is equivalent to 2 pi radians, here's a picture. Since we have this true relationship, it also follows that half of a circle, which is 180 degrees, will be equivalent to half of 2 pi radians, or pi radians. So 180 degrees is equivalent to pi radians. We will use the following conversion factors to convert between radians and degrees. Since 180 degrees is equivalent to pi radians, we have these conversion factors for converting between radians and degrees. How do we use them? Well, this one is specifically for going from degrees to radians. This one is for going from radians to degrees. In example 1, we want to change 360 degrees to radians. Since we're going from degrees to radians, we'll use the conversion factor for degrees to radians, pi radians to 180 degrees. We'll take the original measurement of 360 degrees and multiply by this conversion factor, pi radians, or 180 degrees. Notice that by setting this up this way, we can cancel the degree units here and be left with radians. So we'll have 360 times pi divided by 180 radians, which, reducing this, it comes out to 2 pi radians. Oh, of course, it's 360 degrees, so as we saw earlier, it should be 2 pi radians. Now we know how to find it by computation. Arc length. Arc length is the length of the intercepted arc of a circle. which may also be called the distance between 2 points on a circle. Use this formula for finding the distance between 2 points on a circle. So we'll call this distance S. So we can use this formula, S equals the radius times the angle in radians, theta. So if we want to find that distance, we can if we know the length of the radius of our circle and the angle in radians. Just have to plug it in and simplify. Here's an example. Example 2. The radius of a wheel is 20 inches. It turns through an angle of 2.75 radians. What is the distance a point travels on the surface of the wheel? So we're trying to find S given the radius r and the angle theta in radians. We can use this formula, S equals r theta, to find that arc length distance that the point travels on the surface of the wheel. We're finding the distance between 2 points. So we'll plug in the radius, 20 inches, and the angle, 2.75, into this formula, S equals r theta. Plugging those in for radius and theta, we multiply and we find that distance, that arc length S, which is 55 inches. Then we can round our answer according to the rules for working with measurements. So with rules working with measurements, when we multiplied, we had to round the answer to the same accuracy as the least accurate measurement. In this case, both measurements have 3 significant digits, so the least accurate measurement would be 3 significant digits. So we'd round this answer to 3 significant digits so that it has the same accuracy as the least accurate measurement. Note, if theta had been given in degrees instead of radians, it would have been necessary to convert it to radians before using it to find S. So theta, keep in mind, has to be in radians when you're using this formula for calculating distance. So if we had been given a degree measure for our angle, we would have had to convert it to radians first, then use this formula to find the distance. Sector of a circle. The sector of a circle is the region bound by the sides of a central angle and the intercepted arc of the angle. What do I mean by central angle? It's an angle whose vertex is at the center of the circle. So this is a central angle because its vertex is at the center of the circle. So this region that represents this central angle, that is vertex at the center of the circle, is called the sector. Here would be the intercepted arc. So it's the region between this intercepted arc and this vertex that's at the center. This is the sector. We can use these formulas to find what the area is of this sector for a central angle. We use a different formula based on whether the angle is given in degrees or radians. If the angle is given in degrees, we use this formula to find the area of the sector. If the angle is given in radians, we use this formula to find the area of the sector. Here's an example. Example 3. Find the area of the sector of the circle when the angle theta equals 30 degrees and the radius is 3 inches. In this case, the angle is given in degrees, so we'll use the formula for finding the area when the angle is given in degrees. So that's this formula here. We're going to plug the radius in here for r, and then we'll just have to simplify to find the area. So here is showing putting that radius in for r here. And then we just simplify. By order of operations, we'd square this 3 to get 9, and then it looks like we reduce this fraction here to get 1 over 12, multiply the 9 by 1 over 12 to get 9 over 12 times pi. Plug this in the calculator to get approximately 2.4 inches squared for the area of the sector. Segment of a circle. The segment of a circle is the region between a chord and an arc subtended by the chord. So this line here is called a chord. So the segment is the region between this chord and this arc that's subtended by the chord. So here's the arc of the circle and a chord that makes up this segment here. Note that C represents the length of this chord and R is the radius of the circle. We have formulas here for calculating what this area of the segment would be. We use a different formula based on whether the angle is given in degrees or radians. Really, if we took this whole segment and the area of the triangle, we would have a sector, because this is a central angle with vertex at the center. So if we took the segment and this triangle, it would be a sector. So the area is the area of the sector minus the area of this triangle. That gives us the area of this segment. So this same thing here is the area of a sector if the angle was in radians. So this whole sector, subtracting the area of this triangle, this represents the area of the triangle, that gives us the area of the segment. Okay, let's see an example. Example 4. Find the area of the segment of the circle when theta equals pi over 2, radius is 3 inches, and c, the length of the chord, is 4 inches. Since they give us theta in radians, we'll use the formula for calculating the area of the segment given radians. So here's that formula. It's the area of the whole sector in radians minus the area of the triangle. We'll substitute the given information in the formula and simplify. So the radius was 3, the angle is pi over 2, and c, which is the length of the chord, was 4. So we put 4 where there's c's here and 3 where there's r, because that's the radius. And then we just have to simplify this. 3 squared, which is 9 times 4, would be 36. 4 squared would be 16. These 4's cancel out. Then we have 3 squared, which is 9. 2 times 2 is 4, so we get 9 over 4 pi. 36 minus 16, take the square root of that and subtract it from this. Looks like we could just put all this in the calculator and approximately get 2.6 inches squared for the area of the segment.